All right, good morning. This is like the saddest day of the year, right? Although maybe finals day will be sadder. He's smiling. That's awful. It's awful. All right, a few reminders. I'm out of the office on Monday. I'll be back for the exam on Tuesday. You get extra credit for picking up all your homework graded through 14. I have those available if you want to pick them up after class. Those of you, I think we've given most of them away. Then end of semester evaluations for us is worth a point, extra credit. And those of you that took the ACS exam, there's extra points associated with taking that. About the exam, I guess I haven't looked at the statistics carefully. The high was at 84 on the exam, and the average was around 50, 51 in there. It's a hair above what was done last semester. How many people in here took it? How many said it was would say it was grueling? Yeah. Right. And then I guess the other question I have, I'm thinking down the road whenever this thing's on the market. How many of you think it would have been easier for you if you had your cheat sheet with you? Number of you. Okay. Yeah, unfortunately, because we were testing it, I couldn't violate their rules. Okay, so I have a little tiny bit of material that's new to cover, and then we're going to do a quiz, and then we'll let you guys go. So what we've talked about previously, we've talked about delta G naught, tells us, spontaneity if everybody's present at 1 bar, that's all the reactants and products. We pointed out that we could calculate that from, it's the end of the semester. I'm confused. I don't know whether I've talked about this before or not. At any rate, we know that we can calculate delta G naught. We've talked about Le Chatelier's principle. We've related Q and K to equilibrium. And we talked about colligative properties a little bit. Basically, we've pointed out that it depends upon the concentration of the non-volatile solute. And we talked specifically about ionic substances in water that dissociate. And the identity doesn't count. It's just the concentration of all the dissolved species. And then we've pointed out that the dissolution of that component, the primary impact that it has is decreasing the vapor pressure. And as we've said, if we decrease the vapor pressure, that leads to an increase in the boiling point. And then when we looked at the phase diagram, we saw that that also shifts the triple point and depresses the melting point. So this is the same information that we covered last time. So by adding a non-volatile solute, we see this curve that's the coexistence between vapor and liquid drop. That leads to delta T, all right, an increase in the boiling point, new triple point, and then we see a decrease in the melting point. Okay? All right, and that's all related to the vapor pressure. All right, so some things we're going to talk about today. We're going to show, I'm not going to say we're going to derive, we're going to justify the expression for boiling point elevation. And by the same token, it's the same thought processes for looking at the freezing point depression. We're not going to do that, but it uses the same justification and the same equations. We're going to qualitatively talk about osmotic pressure, not go into any great detail on it. And then the one thing I definitely wanted to cover, and it's only going to take a couple minutes, when we're talking about aqueous solutions of ionic components, of ionic compounds, if you think about what we've talked about up to this point, if I bring a liquid and a solid together and I dissolve it, if there's a strong interaction between those particles, we expect non-ideal behavior, right? That's what we've talked about with regards to liquid-liquid solutions as well. And if you think about it, water's really, really, polar. An ionic substance has, a positive or a negative charge. So these guys have non-ideal behavior even at low concentrations, right? So, how many people have taken Chem 211? Right? And then you think back to Gen Chem when you talk about making buffers. When people talk about making buffers, you start with some, acid, weak acid solution, and you add a strong base to that to reach the desired pH. You don't you don't say, I'm going to take this much acid and add this much base to it, right? And the reason is that the concentrations don't give you that information. It's because they behave non-ideally. So you have to use activities, right? So in our justification today, what we're going to talk about is this relationship that we've seen before. So now we're going to be talking about a solution that consists of a non-volatile solute and a solvent. This is going to be looked at specifically for the solvent. So this is the solution phase or the vapor phase for our solvent is given by its chemical potential when it's pure, and then with this relationship. So that's going to be important. The other thing is, if we just focus on the chemical potentials here, one of the things we've shown is that if we're talking about a pure substance, the chemical potential is the same as the Gibbs energy, all right? And so we're going to let these be the Gibbs energy, and that means that we're going to be able to see a delta G between the vapor phase of our solvent and when it's pure, all right? So that's in solution, and that's when it's pure, all right? Let's see, what else did we want to say? We're going to use the Gibbs-Helmholtz equation. And then in the derivation that we do, we're going to use an identity. We're not going to take the time to derive it, but if we're talking about the natural log of the mole fraction of one of the components, we know that's the same as the natural log of one minus the mole fraction of the other component. And then that turns out to be the same as the negative of that mole fraction of the second component. And that comes from an infinite series. It's something you could do. We just don't have time to do it right now. All right? We're going to use this T NBP to mean the normal boiling point. And then this integral we've seen before, and this derivative we've seen before. All right? So we're going to talk about those as well. All right? Okay, so in section 11.3, we're basically going to talk about T normal boiling point going up, T fusion going down, okay? All right, and some things that we'll do is just remind, you guys did cover these in Gen Chem too, colligative properties, freezing point depression, some of you, all right? So at any rate, in Gen Chem, it's common to see that the change of the boiling point is given by the molality times some constant. All right? So I want to make sure that we just define molality. We're not going to do calculations with it, but that's the moles of the solute divided by kilograms of solvent. All right? And we're going to be calling the solute species 2. All right? So moles of solute. All right? We're not going to use this in calculations, but what we will say at this point is if I have a large mole fraction for component 2, I'm also going to have a large molality for component 2, right? That's the thing that's important to us, all right? Does that make sense? As mole fraction goes up, the molality goes up, okay? All right, so what we're going to be aiming to do is get an expression for Kb, okay? All right, and what we can say is that for our solvent, all right, we're going to look at the solvent first. For our solvent, the chemical potential of the vapor phase is the same as the chemical potential of that component in the solution, as long as I'm at equilibrium, right? Nothing really new there, okay? All right, and then we're going to bring back our chemical potential expression that says the chemical potential of the vapor phase for the solvent is going to be given by the chemical potential, given by is an equal of that component when it's pure plus RT ln times the mole fraction of that component. Okay? All right, and then just to make sure that we know what we're talking about, let me just add one other thing in here. Right? Let me make sure that we make this clear. So this is the chemical potential of the liquid or the vapor phase Because as long as we're at equilibrium, we know that those chemical potentials are the same, all right? So I'm going to be choosing to look at that as if it was the liquid phase, all right? And that's for the pure solvent. So chemical potential of the pure solvent. Okay? In the liquid phase. All right. And then the left side of this, chemical potential of the vapor phase, well, it's also the chemical potential of the liquid phase, but we're going to define it in terms of the vapor phase whenever we're in the solution. Okay? And what we can do is we can say, well, that chemical potential is the same as the Gibbs energy for component 1 whenever we're in the vapor phase. And that's equal to chemical potential for component 1 in the liquid phase plus RT ln mole fraction of component 1. Okay? All right. And you may step back and say, well, I thought the Gibbs energy was going to be the same as the chemical potential if we're pure. If we think about it, the only vapor that I have above this is the solvent, right? Because we have no solute present in the vapor phase. It's non-volatile, right? And one of the things that you can see, and this is where we're going to go, is that this is going to be G of vapor minus G of liquid. Well, that's delta G of vaporization, okay? All right, so we're going to rearrange that. I'm going to write this out explicitly. G component 1 vapor minus G component 1 liquid over RT. All right? And that in turn is equal to delta G of vaporization over RT. Okay? All right, so now what we're going to do is we're going to say, well, we know that this, the differential of this with respect to T is going to be given by delta H over T squared times 1 over R. Okay? All right, so that's what we're going to write down below. This is going to be 1 over R times the derivative of delta G vaporization over T with respect to T, and that will come out to be equal to minus delta H of vaporization over RT squared. Okay? Right, that was a substitution of this in for this. Okay? All right. And then what I can do is I can say, well, now I've got this expression, so I can multiply both sides by dt. I have dl n x1, and then this expression times dt. We're going to integrate this. We're going to integrate it from x1 being 1. And when x1 is equal to 1, that's the pure solvent. Okay? So we're basically saying, you know, what's happening if I'm going from pure solvent to adding some solute to the mixture, to making a solution, all right, to natural log of x1. So that gets me the left side of this equation, all right? And then that means that to the right side, we're going to integrate temperature, all right? And this is going to be from the normal boiling point of the pure solvent to whatever the boiling point is of our mixture, all right? Does that make sense? Okay? All right, and then the integral of this, well, natural log of 1 is 0, so this left side goes to natural log of x1 only, and then I've got what we've seen before. We can pull out delta H over R in front of the integration. That gets me the difference between the reciprocal of the temperatures, all right? So I have this expression on the right side, all right? All right, so this is the identity that I mentioned at the outset, that the natural log of the mole fraction of our solvent is the same as the natural log of 1 minus the solute. And this is going to be the same as minus x2 as long as it's a dilute solution, if x2 is small. All right? So ln minus 1 minus x2 equals minus x2. Okay? All right, the other thing that we can state at this point when we look at this expression, so I've got, here's my delta t, all right, so that's going to be important, all right, and then we've got this t squared in the denominator. What we can say is that as long as we're dilute, the delta t is small, and therefore t is approximately the same as the normal boiling point, all right, and that shows up in the denominator then. All right. Okay, and because we're interested in looking at the change from the pure solvent to the mixture, we're going to take the temperature of our mixture minus that of the pure solvent. So that means reversing this. Right? Everything else remains the same. I'm missing a negative sign here. Okay. But this basically is T final minus T initial. All right, which is the same as delta T. Right? And I've got a negative all the way through, so I can multiply through by minus 1, and that gets me a positive and a positive and a positive. All right? All right? And then what I can do is I can rearrange this and say, well, that means that delta T is going to be given by R times the normal boiling point squared over delta H of vaporization times the mole fraction of the solute. All right? And if we think about that, what this means, this is a constant now, right? Normal boiling point's a constant, R is a constant, and delta H of vaporization is fairly constant. So this is a constant. Please write. Right? And because x2 is proportional to m2, this justifies the equation delta T equals KB for boiling point delta T. Okay? Does that make sense? All right. So we've shown where this expression comes from. Fairly straightforward derivation. Okay? All right. We could have done exactly the same thing, but instead of looking at delta G for vaporization, we can look at delta G for fusion. And we still would have the same end result. All right? So we could do the same derivation the next time around, but now it's going to be in terms of the delta H associated with melting. All right? So this will be delta H. Whoops. I'm looking for delta T. So it's going to be R T squared now of the melting point, fusion, divided by delta H associated with melting times x2. All right? And then when you do this derivation, you find this that comes out to be negative. Okay? Yeah?
Why is delta T equal to KB delta T?
Oh, yeah, it is. M2. Sorry about that. X2 proportional to M2 and vice versa. All right, thank you. Okay? All right. And again, this is going to be a constant, and this is proportional to the molality. And so we can say that delta T is equal to minus the constant associated with melting. Let me make sure how it's symbolized. Fusion M2, all right? Okay? All right, so we've derived these expressions, or I would say pseudo-derived. If you're interested in going from here to here, that's all worked out in detail in the textbook. But it's just, how many people remember doing calculations involving conversions from molality to molarity, and they're not fun. So it's just not worth our time, right? We want this to be fun, right? Okay. All right, I've already talked about this earlier. This is where it shows up in the book and in the lecture notes. Okay, so the next thing I want to talk about a little bit is osmotic pressure. And as I said, we're going to keep this pretty qualitative and pretty simple. All right. So in this situation, what I've got is a water and an aqueous solution on this side. So this is sucrose. This could be a sodium chloride solution. It could be a solution of any non-volatile solute. All right. And then what separates the two is a semi-permeable membrane. And semi-permeable membranes allow the solvent to pass through, but nothing else. All right. Okay. And if you start out with this situation with the two levels exactly the same, that says the pressure on both sides is the same, right? What we would expect to happen if I didn't have the semi-permeable membrane here is that I would get mixing between the two, right? Because it's going to have the delta G of ideal solutions driving it, right? And then if I have like sodium chloride in here, there's also going to be the energy portion of it driving it. So there's a driving force for mixing, all right? And so the driving force for this is going to be delta G of mixing, which is going to be related to, as we've seen previously, delta S of mixing from the universe's point of view, okay? All right, so because it's trying to get the same concentration on both sides, and when I put this limit, this semi-permeable membrane in here, the only thing that can move is the solvent. So if it tries to get the same concentration on both sides, which way is the solvent going to move? It's going to move to try to dilute this, right? And that causes this side to go up. And then we have a pressure differential, and that's what we call osmotic pressure, okay? Does that make sense? All right. So I don't want to be rude, but it's texting and focusing on the stuff. It's distracting to me. All right. Does that make sense? Osmotic pressure. All right. And then just as a practical point of view, how many people have heard of reverse osmosis? Right. So for reverse osmosis, you start with whatever your mixture is, and you put a semi-permeable membrane there, and you apply pressure to drive it in the opposite direction. Right. So you have to go reverse delta G. You have to put energy into the system to get the pure solvent out of it. Okay. All right. And this part should feel pretty good. We're going to cross that out. We're going to cross that out. It's all pretty straightforward, but we just don't have that much time. All right. And then the last portion I wanted to talk a little bit about are aqueous solutions of ionic substances. And I talked a little bit about this at the outset. So, if I take sodium chloride, I dissolve it in water, the sodium chloride dissociates to form sodium ions, chloride ions. I have water molecules that are very polar. I have very strong interactions between the water molecules and the cations and the anions, right? There's something called ionic strength. How many people have heard of ionic strength before? Anyone? No? Not talked about in Chem 211? No? All right. So it's a measure of two things: concentration and charge magnitude. In a solution. Right, and I'm going to, just to make it clear, I'm going to put in parentheses, meaning you don't need to know how to use it, but I did want to indicate how you can calculate it. All right, so it's basically going to be the summation over all the ions of the concentration of the ion times the charge of the ion squared. Okay? Right? I'll close the parentheses in a second. But basically, this is squared because I can have positive or negative charges, and this is, for sodium chloride, this would be +1 squared, and then whatever the concentration of the ions are. And then for the chlorine, I'd also have to include -1 squared, right? And it's pretty clear that the larger the charge, that's going to increase the ionic strength rapidly, all right? All right, and then this table is in terms of ionic strengths. That's why I wanted to talk about that, okay? All right. And what we recall is that gamma, the activity coefficient, has what value for an ideal solution? 1, right? And so what that says is that if it deviates from 1, I have a non-ideal solution, okay? And this is just a table filled with ionic strengths or activity coefficients. And one of the things that we see is that even at relatively low concentrations, I see significant deviation from 1. Okay? And so what that tells us is that if we're dealing with aqueous solutions of ionic substances, they behave non-ideally, and you have to use activity in doing your calculations, right? Oops, activities. All right, so when you go to do pH, everybody's been taught pH is minus the log of the hydronium ion concentration. It really should be minus the log of the activity of the hydronium ions. Okay? Does that make sense? All right, so that's pretty much all of the new material. Any questions before we deliver the quiz? Okay. All right.